So this is what I did last time at the very end to interpret what is the interpretation of the Riemann sum or Riemann sums of these, specifically not even the Riemann sums but even this area under the graph. What is its meaning? Is there a tangible meaning to it? Unfortunately, the physics is more complex here and less vivid than the one about flow. Okay, so you can actually see the water passing through the gate, and then like this, and then that prism over there is what we realize to be the amount of water that has passed, and then the that volume corresponds to that area over there, and that's it. And so that's why the volume is equal to the area, and that's why it's equal to the integral. Okay. Now we end up with the same Riemann sum when we do forces. Okay, so Riemann sums in this case when there are only two sort of short steps with only two values of force. But then this one also can be interpreted in a similar fashion with if you think about particular force, not this applicable to any force of any nature, but if you think about force as for example pushing water through that gate, then the force will be proportional to the mass of the water, okay, and then and therefore it will be larger as you move from left to right. That's explains the picture, and then how much work have you done is in fact the amount of water that you have pushed through. So you can once again see this kind of a visualization of work this time. So the amount of water, this is in fact the amount of work that you have expended pushing it through. Okay, so that explains why mathematics is the same. But so certainly it is, most of the time that's not the case. We cannot really make a connection between two different physical situations that they have the same mathematics. Mathematics is what connects them. Okay, so that's more than an analogy, but not necessarily something that is easy to match. Okay, so once again, that's where we are. We're looking at the force, how it is changing linearly along a certain path, and so the path is horizontal. That's on the x-axis is our trip. Okay, this is our trip, and then at every location of our trip, the force is this. So these are the forces. So the picture is in fact, I'm not saying that it is directed perpendicular to our motion. That's just the quantity of the force. The magnitude of the force is depicted by the arrow. So the bigger, the harder the force is. So there is nothing perpendicular to it, but the picture is remarkably similar to what we just saw. And in fact, I could recycle that picture from last time when we had a canal and a Riemann sum. And so once again, if we think about it appropriately, then we realize that once again we are moving along the certain trip, okay, and certain path. Everything is straight, so there are no deviations. Once again, the force, the blue ones is seen as forces. So these are the forces, depending on the location. These are locations, and these are forces. And then they might be changing continuously. So that's where we're driving at. And then what to do is the same procedure. You sample at several chosen locations. You sample your forces. So that's exactly what has happened here. At different locations, we looked at our force, whatever mechanism that measures the force, and then we put that in the table. And then what at the end we are doing is what the meaning of the picture on the right is those rectangles. What are they? They are multiplication of each displacement. Okay, so that's the displacement. and this is the force at that particular segment of your trip. So the assumption is that for the purposes of approximation, the assumption is that there is no change. There is no change of force during that part of the trip, and so that's why you have a rectangle. Even though it is, like I said, it is sampling, so the actual graph is here somewhere. Our force might be behaving in a strange way, but as an approximation, that's what happens, and we end up with, as you can see here, maybe 5 samples with different lengths, different legs of your trip, and you multiply the displacement every time by the force, you have a real rectangle, which could be negative if the force happens to be pointing in the wrong direction against your motion. So, and that gives me the Riemann sum, just as before. So, let me f of ck times delta x k, the displacement, the sampled force on that trip, and then you add all of them together, and you have the Riemann sum. Okay, progress the same way as before. Take the limit with delta x going to 0. The end result, the Riemann integral. So integral from a to b, that's our trip, from a to b, straight line always, f of x delta x dx. That's all. So w. Representing the work of the force, y equal f of x, along the trip from A to B. So later on in Calculus 3, the trips might be on the plane and it might be circular or in kind of tracing some kind of complicated path. So far, we're still in the one-dimensional situation, so all the trips are along a straight line, and all the forces are also aligned with that straight line. They could only be pointing with or against us, but nothing more complicated is happening just yet. Okay, so that's how that works out. That is, you can think of it as both the definition as well as the formula for computing things. The only thing that I want to compute is similar to this example, the second example. Something more specific to physics, and that is, well, if we just take a spring, like this, and so a spring is attached to the wall, and then there is with no friction, let's say, so mass m. And we pull it. We pull the object against the spring, and we will ask ourselves what is the work. Of the spring. Okay, so hypothetically, if we have here maybe this is the equilibrium, and we pulled it, well, let's say at A, and we pull it to B. Okay, the only thing that is for us to worry about, so that this is our trip along the x-axis. That is our trip. We are working against so the work will be negative, but we're only interested in the magnitude. So, so the only thing that remains is for us to compute is what is the force. before we get to work of the spring. But we're talking about the force of the spring. What is the force of the spring? If anybody remembers from physics? No, you're talking about that specifically applies to, well, that is generally applies to everything. That's Newton's law, specifically for a spring. Remember how the force of the spring changes as you move the object away from the equilibrium.
The force of a spring is kx.
That's right. So anybody can elaborate what this means?
K is the spring constant.
Okay, and x is? The position relative to the equilibrium. So in fact I put 0 here, so in order for us to see, well actually, well it's not kx but rather, no, that will be the work. No, they will still the force. Oh, it's not the force kx but negative kx. Negative kx is the force because it pulls in the opposite direction to our motion. So moving from 0 to 1, the force is pulling in the exact opposite direction. Okay, so that is the whole story is right here. Hooke's law, who was a contemporary of Newton, I believe. Okay, so once again, so the force is proportional to the displacement, and it is pointing in the opposite direction. Okay, so K is that constant that depends on how stiff your spring is. Okay, and then now we can, with this, it's really not a challenge at all to compute the work. So if we move b units to the right or to the left, it doesn't really matter. Our work is the integral from 0 to b fx dx, which is integral from 0 to b negative kx dx. Integration of a linear function is uncomplicated, so it will be kx squared over 2 from 0 to b, negative. And so the total is simply negative k b squared over 2.
So the mass doesn't matter whatsoever?
Hold on a second. Mass doesn't matter.
I don't know. I haven't had physics yet.
Well, the formula is correct.
It shouldn't matter until you start messing with the friction.
Yeah, the friction will depend on force, on mass. Yes.
Or would it apply to?
No. Yeah. It's so it's.
Mass applied to the energy involved with the system?
No, I'm afraid I can't speak of the energy here. I'm just thinking about the original question is, so how do you explain that Hooke's law essentially? How do you explain Hooke's law that the force of the spring and the work of the spring is independent of the mass attached to it? It makes sense. You remember the mass comes into play when you bring in the Newton's law and you actually want to compute the acceleration, for example. Okay, but the force remains the same. So the force is what the spring has and what it applies to the object. So the bigger object will be affected less with the same force, and vice versa. The small object will be pulled harder and faster. And so then the displacement certainly will depend on the mass. But if the displacement is given, then yeah, it is independent of the mass. It was the way I understand it. As you can see, it's interesting that the answer is the work is always negative. It doesn't matter you pull it to the left or to the right. It doesn't matter because either you will be working against. So either pulling or pushing has the same effect. Well, which is kind of the information about that is contained in Hooke's law, right? So to the left or to the right, even though the nature of what's happening is different. You seemingly pulling or pushing might be different, but mathematically it's the same force, and the work is also the same. Well, the force does change the direction, but the work does not. Okay, so that's what we have discovered. As you can see, the work is proportional to the displacement, and proportional to the square of the. No, it is proportional to the square of the displacement and proportional to the spring constant K. Okay. Okay, so usually that's what you face when you have a problem about work, and every single time that we have dealt with all these applications, a bunch of them, the end result is very, very simple, like this. Nothing about a very simple integral with maybe slight complications when you're computing the length or you are doing the center of mass. Okay, so the integrals are slightly more complicated, but it's still nothing but an integral. And so if the function is manageable, you can just plug things into the formula and you have your answer. Some things are more complicated. There is no formula. So and that work. Some of the problems about work might be more challenging than that. So that's what I want to consider next. Okay, so once again, this is nothing. The last example is nothing but a formula. It is based entirely on that analysis above, and just any force, continuously changing force, will produce, will require nothing but the application of that formula at the top. You integrate the force along your trip, and you have your work. But sometimes things are more complicated, and there is no formula available right away. So let's start with this simple example, bricks. Lifting bricks, stacking bricks. So suppose I have 4 bricks, and what I want to do is I want to stack them up. Okay, so from 4 on the ground, I want to bring them and put them in a stack. Okay, so what is the challenge? There is no continuous change or anything that other complications of that nature. The problem is that different. It's not the force that changes. That's the major shift that we are taking here. It's not the force that is variable. The force is the same. Each brick is affected by the same force of gravity, identical gravity. What is changing is the trip. So once again, in the previous example, it was, let's say we were talking about the spring again. Then the force varies from location to location, but the trip is given. Okay, now the opposite. The trip varies for different objects even though the force is the same. So because the first brick will not take any trip whatsoever, that's the first one is here. The second you have to lift it up here, the third has to be lifted higher, and the fourth you have to be lifted all the way up. Okay? So same force, different trip or different displacement. Yeah, so it is quite a bit different. So the main challenge is that formula we just discussed is not applicable. So once again, take a look at the formula. The work of the force y equal f of x, which indicates that the force is variable over your trip, but along the trip from A to B. So there's some object affected, which is nothing special about it, just a point possibly, takes a trip from A to B. At every point of the trip it is affected by a force, and then you just, how do you find the work? You just integrate or add up all the forces that have been involved. Now there is no difference in the force. So once again, they're identical bricks possibly, and they arrive to the same, but the trips that they take are different. Okay, so then it is uncomplicated. Say, let's say the force says is equal to F. So same force, constant. Okay, so that's my force. And now, but the trips are, well, I numbered them 1, 2, 3, 4, but actually the trips are, let's say 0, 1, 2, 3, right? So then the work is some of these, or rather you multiply the work of, how much work do you need for each of these to be placed where it belongs? It will be 0 times 1. Hold on, in the right order, let me put it in the right order. The right order is the force times the trip or displacement. Okay, so for the first one it will be the force is F, the displacement is 0 for the first brick. It's not going anywhere. The second one, the force is still the same, the displacement is 1. So you have to lift it 1 width of the brick up. Okay, the third one is F times 2, and the fourth one F times 4. Total is F times 7. Okay. Once again, the main problem is that it does not fit into our formula, so we would need a different formula. So that as long as these are bricks and they are separate and you know how many, you can just do this. That's the idea of how we handle it. It is the problem becomes complicated when you're moving something that is actually infinitely divisible. So unlike bricks. A stack of bricks, so you divide, you don't divide bricks furthermore. But water. Water is to be, when it is to be moved, it is, like I said, infinitely divisible. So a similar problem to this is when you have a tank. So the picture might be, in fact, similar. Well, so there's a pool of water, and you want to put it in a tank. Okay, like this. So, which means that every you can think of once again about layers. So these are certainly not bricks, but if you start thinking about layers, that certainly helps. So every layer starts at the 0 level at the bottom, and then it has to be lifted. But it takes different trip. Every single one takes a different trip. Okay, so that's a starting point. You are not doing the whole thing at once, but rather slice it up into pieces, and then see how much every one of them, how much trips it takes. So let's say it is 1 by 1 by 1. Doesn't matter. So suppose the height is 1. So the question is how much work it takes to, well, pretty much pump water to 1 by 1 by 1 by 1 cube or tank. Okay, so assuming that everything once again starts at the level of 0, and then it is lifted at a different level, so up starting from 0, starting to ending with 1. Okay, so once again it is almost like bricks, okay, so where is my x-axis? The x-axis will be placed vertically like this. Okay, so because that's where our trips will be taken. from 0 to 1 right here. So that's my x-axis. And then even though the, well, let's just go on with our slices. So the slice to be lifted might look like this. It has some width, which we call, or rather I would meant thickness, h. Okay, so thickness h, and then that is the only characteristic of the of the layer that we care about, because that thickness gives us the volume and the mass. Okay, so you can say this is the volume. Everything is the density is 1 and is equal to mass, and the only thing that we care about is the force. Well, let's say it's the force. Let's say the force is also equal to 1, equal to h. So h gives me the amount of water, and it measures the volume, it measures the mass, and it measures also the force applied to that slice. Okay, so as you can see, it is every slice will have the exact same force, just like with those bricks. But what is different is so that's the force is equal to h, and what varies is the trip, the displacement. So displacements vary from 0 to 1. So the lowest level doesn't go anywhere. The last level, once again, it's like, imagine that the tank stands in the pool of water and we're pumping up from the bottom, like this. Okay, so so what we have here is then well, suppose h. So we have 1 over h slices or layers. Okay, so that's how many layers. They are then, so this is my 0, 1. Okay, so we divide it into little pieces, each with h, and then at this point we're pretty much applying the same logic as we apply to bricks. We can think of those layers as if they are bricks, and then we'll deal with that later, what to do. But at this time, the force that we're dealing with is h. Okay, and then but what is the trip? The trip is x. So this is the trip. So once again, I laid my x-axis on the side finally, so it was vertical. It only vertical because we want it to be, well, we will want to go against the force of gravity. So that's gravity. So we don't want any pointing out in some other directions. Okay, so let's see. So what do we have here now? Okay, so 1 over h layers. Well, let's say n layers. So we have n layers, which means that h is equal to 1 over n. The trip, each of them is taken is in chronological order, will be from the bottom. Let me just list displacements. Are 0, h, 2h, 3h, and h, which is supposed to be equal to 1. Okay? Okay? What's with that clock? Okay, so so forces. I'm sorry. Displacement. Force is the same. Is equal to h. So we are next is work. Of each layer is requires different work because it takes a different trip. Okay, so work is, or R, if you prefer, it will be 0 times h, h times h, 2h times h, 3h times h, and finally nh times h. So I just take my displacements and multiply them by the same by the same force, which is h at the top, as we determined. That entirely determined by the force is entirely determined by the thickness of the layer. Okay, so then what remains is to add them together. Total work is sum of these, so 0 times h plus h times h, 2h times h plus nh times h. Okay, so well, clearly all of these are squares, so it will be, if I factor h squared out, what am I left with is 0 plus 1 plus 2 plus n. Okay, so hold on a second. Where am I moving here? W. The fuck is W? What is W? There's no W. Okay, so I need to, in order to finish this, I will need to get rid of either n or h. I think I will get rid of n, because n and h, as you can see, they are related to each other in that manner. But whatever we're producing, this is not the total work, but rather a total work of approximated work, because we sliced arbitrarily our tank into those layers, and that's why we gotta have a limit eventually at some point. At this time, so h is equal to n is equal to 1 over h. Okay, let me try to continue this and finish in this manner. Okay, the summation, I'm not sure if you have seen this summation. Have you seen the summation before? The sum from 0 to n? Like this. Well, let's divide more. Okay, so we're adding 0 to 0 plus 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7. Okay, so that's what I want to compute, and the idea then is to observe that how do you add those red circles? You take the whole thing, which is n by n. So you have the total of n squared cells. You have n squared cells in this box, and then what do? You compare to this green and red. You can see the relation. Like no, not the last one. Shit. Like this. Okay, how many compare the red one to green ones?
N squared minus n?
N squared, close. Well, what I'm driving at is that my n squared cells in that square, n by n squared cells, they are split into 3 parts. green ones, red ones, and the diagonal ones. Okay, and on the diagonal, how many do I have on the diagonal here? I have n of them. Okay, so this thing is equal to, suppose I have x number of red ones, then look at it, I have just as many x the green ones. Okay, so the total then is what? X plus n. Well, it's almost correct. It's actually n plus 1 over here. N plus 1. N plus 1. So because it starts with 0, then we have actually n plus 1. Okay, so x is n plus 1. Okay, so long story short, this summation is equal to n plus 1 over 2. I do think that you may have seen this before because it is used early on in the Riemann integral when you do integration with Riemann sums, and when you do a linear function and you're computing the area under the graph of a linear function, that's what you end up with. And you end up with a Riemann sum that looks exactly like that expression, and then you have to get rid of those dot 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 things for y, because you want to do you want to take a limit. Okay, so the limit of Riemann sum is the Riemann integral, but you don't know what how to take the limit of expression like this when you have dot 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 there. Well, fortunately, there's the shortcut, the formula that tells you actually what the answer is, and that's what we just did. Okay, the answer is n times n plus 1 over 2. Okay, so so h squared, and let me see what happens here. So it will be n is equal to 1 over h, so it will be 1 over h times 1 over h plus 1 times h squared. Okay, what do we get here? Over 2. Okay, so what do we get here? I multiply by h, I'll have 1 plus h over 2. Okay, and with h going to 0, the answer is 1/2. It seems a little bit like magic, but really it is just we solved the same problem with just switching things between what is, we have only one variable. We're dealing still with functions of one variable, so we cannot vary simultaneously the force and the displacement. So we solved the problem when the force was variable, and we ended up with a neat integral. Okay. Now we change gears here, and we assume that this time the variable part is not the force but displacement. Okay. So that was one of the examples of what has happened. Of how it happens. So once again, we are moving the layers of water one by one from the bottom to the top, and that's why the trip every time is taken is different for each of these layers. And then I have n of those layers. The displacements, as you can see, do vary from 0 to h, to 1. That is, it's like over here, I take n steps along one layer at a time, and I reach the highest one to compute work it takes to move each of these layers separately. I have this, okay, multiply the same displacements by h, the force, the thickness, and the total work is just to add these together. And then through the magic of algebra, I simplify that expression to end up with this. Okay, so this is how much it takes to move n layers of thickness h from as many as necessary, different values. But if we now assume that as we want to take into account the continuous nature of this function, the trip is changing continuously, the distance of the trip changes continuously, then we have to set h go to 0, and the limit is 1/2. How do we know that the answer is correct? It was a bit complicated, but certainly easy to make a mistake. How do I know that the answer is correct? The work is 1/2. What's so special about 1/2? Let me try to put it this way. So this is my water on the ground level, and in the beginning, and at the end it is this way. And this with this there, this is 1. So what's the importance of 1/2? Midpoint. Okay, so why does it matter?
Helps you determine your steps.
No, what I mean is some kind of common sense. Forget about mathematics, and what is the common sense about this problem? How much does it take for you to move everything from level 0 to distribute it equally from 0 to 1? Well, instead of, we had already 4 bricks, and then imagine that instead of bricks you have tiles, and how much?
The average of the distance.
Right, exactly. It's simply the average of the distance. The average of the distance for the bricks, tiles, or layers of water to take a trip. And it is halfway, so that's why the answer is 1/2. Another way to look at it, ask yourself by how much does the center of mass of water moves. The center of mass was on the 0 level, and then it became on where is the center of mass of our cube on level 1/2. So that's once again the trick. The water actually, if you take as one chunk, the work actually takes to move everything is the same as the work to move its center of mass. Okay, so the center of mass has been lifted from 0 to 1/2, and that is the work. Okay, so it is totally common sense, right? So move a person. How do you evaluate the work it takes to move a person, which has a complicated shape? Well, just center of mass. Look where the center of mass is. The mass, center of mass, and that's how much work it takes. Okay. So even though different parts of the body would have to move different distances, but we don't care. We only care how much the center of mass has to move. Okay, so that idea is hidden in this computation. So you can imagine that, and I try to confuse you. What if we, instead of having a cubic tank, what if it is a cylindrical tank? Same story, same problem about the cylindrical tank. What's the answer?
1/2.
It's still 1/2, right? Because once again, the center of mass moves 1/2. Certainly, it does not solve the problem in terms of general problem. It is a shortcut which works when it works, and when sometimes it doesn't work. Or here's an example when it does not work. I think. What if it is a spherical tank? No, as long as you know where the center of mass is, it works. Its shortcut works. So it is when it is misshaped tank of unknown nature, unknown center of mass, then you don't know where the center of mass ends up. So you have to go through this computation. But it still works. If this works, that works, all of these works. They will be every time you move your center of mass from the bottom to the center. Center vertically.
What about a pyramid?
A pyramid, well, yeah, okay, so pyramid, it's not obvious where it is. Horizontally, it's clear where the center of mass is, but vertically, it's not. That's a good example. So pyramid tank would require all this work to do very carefully. This way or upside down, questions frequently is posed as in the form of a cone. A cone filled with water, and how much does it take to fill it? A cone, maybe upside down, just to keep it straight rather than thinking about the tank. You have a cone, and you're filling it with water, maybe like this. Okay, so as you can see, the trip varies, but also the shape of the amount of water you have to move every time. The layers have different shapes, so that's also creates a problem.
Like it fills up faster at the beginning.
Right.
Than it does at the end.
Yeah. So as you can see, there will be variability both in the distance and the force is the same, but the amount of it is different. So that brings me to the next question, which is the average value of a function. Another angle on the issue of central mass in a way, except we're not going to be balancing our function on the like this. That was the initial idea. Now we are approaching it from a different direction, and that's the average value. Average value meaning value on the y-axis. So these are where the values are. Okay, so we're not averaging x anymore. We're averaging y's. So and that is done in a different way. So that's why that does not apply anymore. So average value, we know if we have x1, xn numbers, the average is, what's the meaning of an average of n numbers? How do you average things?
The sum of the x's over n.
Over n, right. Okay, so and then imagine that instead of having a few values like spread out n or 10, 100, it is changing continuously. So the values of x are changing continuously. There are infinitely many of them. So you cannot add infinitely many terms and then divide it by infinity and hope that something meaningful will come out. So we'll have to analyze it from scratch pretty much. Okay, so I'll just stop here. Yeah, okay, thank you.